Ron Wilcox, KF7ZN. Over to you.
Thank you very much for that very gracious introduction. Yes, as Ed noted, I had a career with Mountain Bell and then US West and then Quest, specialized in something called air pressurization. Was laid off 3 times. Management, when they did the purges, got tired of the layoffs, and we had lost most of our retirement. Decided to reinvent myself, went back to college, got into a nursing program right off, and got my RN degree, and I've been doing that for a while. So that's kind of a quick type of a history. And again, you can look at my QRZ page. It has a lot more information there about some different things and some things in my life. So why this topic? I did a lot of presentations when I was with the phone company and with my role in management. I did a lot of presentations in my community, and I did a lot of presentations with my church and other things. And so I enjoyed it. A few years ago, I was at a ham radio convention, and as we left a presentation by some of our more expert propagation experts, they came out and they said, "Boy, that was interesting, but I really have no clue what happened." And the other one said, "Yeah, I do that a lot. I nod my head, but I don't really know the details. I'm not that much into it." I began to ask around, and I found out that unless they were really had that science background, that a lot of people began to tell me and said, "Well, I don't understand what some of these terms mean, but I kind of get the gist about what's going to happen with propagation." So I made this, presented it at a ham radio convention. It was very well received. And so I've been presenting this to clubs all over the United States, and did one international along with my other presentations. So the reason I do that lead up, this is an introduction. This is not an in-depth physics, ionospheric physics. This is to help the common lay ham radio operator to understand the terminology and the basics before going into some of like Carl, not K9LA, and some of these expert people. So with that, and we will get started. So Fairlawn Amateur Radio Club, 65 years plus counting. That's just absolutely excellent. I always try to do a little bit of research to know the club and the organization. So that's great. Let's talk a little bit about the sun and take a visit to the sun and to the ionosphere. This is basic, as I said before. Let's talk basically about the sun itself. The sun sits 93 million miles from Earth. If you were to fill the sun with Earths, you could fit in 1,300,000 Earths inside of it. The Earth makes up 99.86% of all of the mass found in the solar system. You have the core of the sun. This is where you have a fusion of hydrogen into helium. This creates a tremendous amount of heat and a tremendous amount of energy. We're going to talk about plasma a couple of times in this presentation. It's important to know, or at least have a basic understanding. Plasma is the 4th state of matter, and it's a gas in which we have ionized particles or charged particles. Now, the energy we referenced to a second ago inside of the sun, it will take up to 100,000 years for that energy and those magnetic fields to work their way from the core and the inner aspect of the sun to the surface of the sun. Now let's look at the temperatures. Now the core temperature in the sun is 29 million degrees. The surface of the sun averages about 18,000 degrees. And then a little bit above the surface, it goes back up to 2 million degrees. I'm not going into any detail about that, but with the recent satellite that was launched, we now know that that is due to magnetic fields and their energy and what is happening to them. It's a very recent discovery why the increase. There were some theories, but we now know why. Important to understanding propagation and the effect on the Earth is solar wind. Solar wind comes out continuously from the sun in all directions, and it is atomic particles. It expands outward, and it's a never-ending flow, basically, of the coronal plasma. You have two different speeds. You have one speed that's called the slow solar wind. This takes roughly 4 days to come to Earth. That's an average. And you'll also hear about the fast solar wind. This one takes about 2 days before it to arrive at Earth. The slow mainly comes from the middle latitudes on the sun, and it only goes 200 miles in 1 second, just barely putting along. The fast solar wind is mainly found over coronal holes, and it is more at the poles and the higher latitudes of the sun. So when you see pictures, a lot of times the different, like Dr. Scove, Tamitha Scove, and others will show pictures of the sun. When we talk about the coronal holes, you can see these dark areas. That's what they're, and they're not really a hole, but because they were darker, many years ago, people thought that was a hole in the sun. And there's another artist's conception of that solar wind coming out from the sun and its effect on the Earth and kind of deflecting around the sides. Now, let's talk about sunspots. Every ham radio operator loves to talk about sunspots. Some of the early theories when they first discovered sunspots was, oh, it's a speck on your telescope. There was actually some editorials in some writings back in Galileo's time and some others in which they said, you have dirty telescopes. There were others that theorized that the huge mountains on the sun, they were colder than the surface of the sun, and sunspots were mountain peaks that you could see. Other writings say that the sun obviously is surrounded in clouds, and every once in a while there's a hole in the clouds of the sun, and that's what a sunspot is. So sunspots were even anciently, the Babylonians and the Chinese, and that's a whole different presentation. They actually saw sunspots and noted some of them. So this wasn't the visualization of sunspots was not a new discovery, but that what they did and their association is fairly new. Cycles. It's an 11-year cycle with a maximum and a minimum. A complete cycle with the reversal on the sun is about 22 years, and that can vary. We're talking averages here. So which cycle is the most intense on record? As far as we know, it is cycle 19, which started in 1954. One of the smallest cycles in the last 100 years. Yep, you've got it. The one we just came out of. The famous cycle 24, the bane of ham radio operators. And then, of course, which one are we in now? We're in 25, which is interesting the way it's going. And again, whole nother presentation. There's a whole presentation just on cycle 25, some of the different theories and why of the different theories and what they're doing. Here is 400 years of sunspots, counting sunspots. We have something that you've probably heard, most people have, is called the Maunder minimum, in which there was a long period of time where there was very, very few sunspots. And I believe there was about something like, I think it was like 28 or 32 years where a sunspot was never observed on the sun during that time period. There's some interesting research quasi-theories about effect on the Earth and its climate. Nothing proven. So you may hear some things on that. There was another minimum that started, I think it was around 1810, called the Dalton minimum. And then we have some maximums. And we're going to talk about those quite a bit more when we get down to the Earth and their effect on the Earth and some really interesting things that happened, like during the Vietnam War and some other things. So where are sunspots located? At solar minimum, sunspots will start in the middle of the sun. If you see the one cycle 23, you'll see that that's where they start. And then as the cycle progresses, the sunspots tend to go down towards the equator. And they will move east to west, and they are generally visible for about 13 days before they go on the backside of the moon. Of course, now with the stereo satellites and such as that, we can have much better visualization of them. If you'll notice, the sun, when it rotates, at the equatorial level, it rotates a lot slower than it does up in the polar area of the sun. This is really important about the formation of sunspots. Magnetic fields under the surface are longitudinal. In other words, they run north and south. But because we have these different rotational speeds, these magnetic fields start to bend and they start to distort. And they start to go into an east to west direction. This develops tremendous energy. And these magnetic fields are under the surface, like I said. They will sometimes break through to the surface of the sun, and then you'll get these huge magnetic loops and a cooling at that region. So if you notice here, we're basically north and south. Then we start to have bending, and then we get more and more bending of these magnetic fields. And remember, these are under the surface. And then you'll notice there the magnetic fields, how it's broken through the surface of the sun. And this magnetic field, you're seeing the sunspot down at the base at the surface of the sun. Size, they can go in size from just a mere few hundred miles to up to 250,000 miles across. Now, why are they dark? Well, they are 30% cooler than their surroundings. And here's something important. They're visibly dark, but they are radio loud. You'll sometimes hear about the SSN, the smooth sunspot number. It's not really used a lot for what we do, but you do hear about it in some of the propagation forecasts. If we were to look at daily and monthly numbers of sunspots, they're spiky. They're like all over the place, huge fluctuations. So what's done is they take data 6 months after and 6 months behind a date, and they will take all that data and call it a smooth sunspot number. And this number is really fairly subjective, but it does give us at least an average or a starting point. Sunspots, now as they begin to increase in number, we start to see an increase in ultraviolet radiation. And voila, we have improved propagation. And the higher bands open up as the ultraviolet increases ionization in the ionosphere. We'll look at that in a minute. It's actually the area around the outside of the sunspot is where this UV radiation actually comes from. Let's talk about solar flux. You will also hear about the solar flux and its level, and this is important. The sun generates a lot of radio energy in the microwave range. This is called solar flux. It was very shortly after World War II, it was discovered that the radio energy that they were seeing was very closely correlated to the number of sunspots present. The microwave frequency is 10.7 centimeters. And so you'll also hear this thing called the 10.7 centimeter flux index. but usually you just hear it called the solar flux. And it gives us a good indicator for long distance communication. However, something important is that the solar flux does not cause any ionization. It is just something that is a corollary that is an interesting tool. It's reported daily. Values go from 60 to 300. Low values, typically conditions are not very good, and we're talking about propagation. During the peak of a sunspot cycle, some values can be over 200. It takes a few days of these higher values before you see the conditions improve. It doesn't just happen immediately. Now, let's talk about solar flares. These are cool. A brief, intense, incredibly high energy eruption from the sun, but this is important. They don't have a lot of material. Very commonly, you will hear people confuse or mix up a solar flare with a CME. A solar flare does not have a lot of material, and it will have X-rays, radio bursts, and mainly protons and electrons. A solar flare is caused, those magnetic field lines that I was mentioning, if they start to tangle or cross with each other or become reorganized, this will cause some of the magnetic field and energy associated with it to break off and head towards Earth. Solar flares are very, very fast. They're close to the speed of light. In fact, 8 to 10 minutes and they're at Earth. You cannot predict on something like that. And they can affect power grids, satellites, and radio communication. They are often associated with our next topic, which is CMEs, which is a coronal mass ejection. Now, solar flares have different classifications. You'll see this all the time. We just had some M and X flares over the last few weeks, created a lot of conversation and interesting news articles on the space weather. Dr. Scove had a lot of stuff, and other sources have been talking about it. You have a C, which is the smallest and really doesn't affect things much. You have an M, and then X is the largest, and then you can actually go over X. And once you get to that level, you're going to start having an impact. Now, this is like the Richter scale for earthquakes. Each letter represents a 10-fold increase in the energy output. Now, let's talk about CMEs. These are large expulsions of plasma and magnetic fields. They can eject billions of tons of coronal material. So that's a lot. They take 2 to 3 days to reach Earth. This is what causes your auroras that you see. Some of the early scientists said that lightning would inject electric fluid into the telegraph lines. But then when they started having problems with some of the telegraph lines and there was no lightning, but astronomers, particularly the heliophysicists and those associated with the sun, began to see these large disturbances on the sun, and they began to realize that it wasn't lightning that was affecting the lines. This is a coronal mass ejection, and you can see how much material is in that. And another one. And you can see the waves, the fields, the magnetic fields holding some of that energy. And this one is about ready to split off and be thrust away from the sun. And like I said, they cause auroras. And the different colors are caused by oxygen and nitrogen. And I'm not going to get into that now, but that's a very interesting topic, how the different colors and how it's impacted by the different materials found. Aurora, the first written record that we have is found in 800 BC from China, where they talked about auroras. There are many references, particularly in medieval times and the time of the Romans, where they talk about dragons in the sky. They thought that the colors and the way the colors waved and moved that this was caused by dragons. And that's why they called auroras dragons in the sky. So in 37 AD, Tiberius Caesar saw the aurora. It had come so low, and he was convinced that a large city to the north was on fire, and he began sending a lot of soldiers up to help fight the fires. You'll see many references in the writings back of that time, and particularly in the medieval times, and you'll read bad omens, bad feelings, created a sense of foreboding for things to come. They weren't understood, and many times they gave them, like I said, dragons and bad omens, and they attributed it to different things rather than science. So let's talk about some of these storms. May 1921, it happened on May 13th to May 15th. It was part of solar cycle 15, and it was near a sunspot minimum. It sparked fires worldwide. At different places, the maximum measurement on the some of the telegraph and phone lines was 1,000 volts. Grand Central Terminal caught on fire from this, and this storm has been known now as the New York Railroad Storm. The estimated size of the sunspot is 94,000 by 21,000 miles. In Geneva, Switzerland, all of the electric trolley cars at the same time came to a sudden stop. In Sweden, a telephone station was completely burned out and gutted. For AT&T, the transatlantic cables, there was 3 of them. 2 of them were damaged, 1 severely. There were impacts globally reported of disruptions in Australia, Brazil, Denmark, New Zealand, Norway, United States, all over the place with this particular storm. 1972. This one was not just an X class, it was an X20. And it produced white light, which is very rare for a CME, a lot of gamma rays associated with it. It destabilized many portions of the North American power grid. Now, one thing interesting, and the records from the military and the Pentagon were just released about 10 years ago. So this was kept, I guess, I don't know if the word secret is appropriate, but it was not available for a long time. August 4th, 1972, when this hit, naval mines near Haiphong began to detonate. The Navy sent emergency messages back to the Pentagon saying, we are under attack. 50 naval mines exploded. We now know that it was because of this CME that caused it. At that time, they had no idea. This CME's transit time from the sun to the earth is the fastest that we are aware of, 14.6 hours, and it arrived. Storming continued for quite a while, for days, and much of the auroras were a bright red, which is a fairly rare color and is usually associated with just very extreme CMEs. 1989, we'll just do a couple of these. This is called the Year of the Turbulent Sun. In Quebec, there was a major power failure, and parts of the northeastern US. The electrical power supply was cut off to over 6 million people for over 9 hours. Auroras were seen down to Texas and Florida. There were radio HF blackouts in many places in the world. Many of the satellites that were up were damaged, and many other satellites had to be reset. Now, from March 16th to March 19th, there were 48 M-class flares and 11 X-class flares. This is a picture of a 340 or 345 kilovolt transformer from Canada, and it just basically melted it. I have a picture of the whole thing, I don't include it in this just for time's sake, but I think it's like about 4 feet high. And the CME just totally took it out. And then, of course, the one that we hear talked about a lot, and that's the Carrington event. This is one of the largest that we know of. It occurred in 1859. It reached the Earth in 17 hours. Many newspaper articles and people in their personal journals. Sparks showered from the telegraph machines. They began to disconnect the batteries, and it continued. There were many operators that got burns on their hands. Fires were set, papers were burned on tables, and the average measurement in many places was 675 volts. All over the planet, it began to glow so brightly. On the night side, birds began to chirp. Laborers started their daily chores. They got up. They thought the sun had begun to rise. In fact, there's some miners that were in Colorado that said that they got up and began complaining to each other that it felt like they had hardly even gotten to sleep. And then they realized that it had only been a few hours and that this was this lighting, and they didn't know what it was from. Some people thought the end of the world was at hand. Armageddon is here, ran some headlines. While this was going on at night, many churches opened up for people to come and to pray and worship. Compasses everywhere went crazy and could not be used. And there's a picture of one. Now there's a new one called, and I'll mispronounce this, I do every time. I think it's Miyake, and it's after a scientist at the Nagawa University in Japan. There was a recent article in Scientific American about these. They are 10 to 100 times stronger than the Carrington event. Researchers at this point are pretty sure they have found 3 of them. One is at 71, 76 BC, 52, 59 BC, and 775 AD. I'm not going to go into how they found them or anything. It's quite interesting. And again, there was that article, but it's beyond the scope of what I'm trying to do here. But it's interesting that they have found these events, and there's just some brand new research going on. And this is just in the last couple of years. Seems like the ARRL had something, I think it might have been a QST, also referencing this a little bit. Okay, now we're towards the end. Let's talk about the Earth. The Earth's magnetic field is also called the geomagnetic field. High energy particles from the sun will disrupt our magnetic field. And as it pushes against it, it'll cause a tail on the backside. This is called the magnetotail. This is the magnetic field that will have the tail. Think of a rock in a stream. As the water goes by and you get that little turbulence and tail behind the rock. There's an artist's conception of what it does look like. Magnetometers, we talk about those a lot in HAMSCI, and you're going to see a reference to them. This is a device that measures magnetism, the direction, the strength, and the relative change of a magnetic field at a particular location. We now have some of these available that even people like you and me can put in their backyard if they're in the right, if everything is right, and be able to send this data into a central source. Let's see, there's a lot of information on HAMSCI. I just finished writing an article for CQ that went into it a little bit, talked about it with HAMSCI. So, and with these magnetometers, we can create indices, information. There's quite a few indices, but the 2 main ones that you hear in ham radio jargon is the A index and the K index. And they basically give us an idea of the severity of the magnetic fluctuations in this geomagnetic field, and it's more at the mid-latitudes. This particular one uses a network of 13 magnetometer sites. The K index is measured every 3 hours. And if you combine all of the sites, you'll get a global average. So it's called KP, which stands for K planetary. The KP index itself goes from 0 to 9, 0 being quiet and 9 being severe. 3 or below will indicate good propagation, but you really have to be careful using this as your basis for when you're going to get on and how it's going to be. This is just a tool that can help. And then we have the A index. A index is every 24 hours. It takes 8 K readings. Remember, the K is every 3 hours, so it takes 8 of those, and it's put out as a daily average. It goes from 0 to 400. 15 or below, probably good propagation. And if they do all of the readings, again, we put that P after the letter, and we have a global average, or A planetary. Now let's go to the ionosphere. These are regions. They used to be called layers, but now we're trying to get away from that and call them regions. These regions have the most density in the center and the lowest density at the edges. All regions of the ionosphere have ionization, but each one has specific characteristics. The ionosphere is a plasma. And when we speak of refraction or bending our radio waves, the electron density is the controlling factor. So we have neutral atoms in the ionosphere, mainly oxygen and nitrogen, with a little bit of helium, argon, and hydrogen. Because they're neutral, there is no charge for our radio wave to interact with, and they would just go straight through. But ultraviolet rays have enough energy that they will separate the electrons away from the nucleus. Now we have a positive ion, which is the nucleus, and a negatively charged electron. And here we go now. Our radio wave will be refracted back to the Earth. And again, this is not a seriously in-depth, I am trying to give basics here. The ionosphere, the ionization from the Earth extending up, the density of your neutral atoms is reduced as to how many there are. The less density that you have, the longer the electrons take to recombine. So if you go to the upper parts of the ionosphere, where there are not as many neutral atoms, when an atom splits apart, it'll be longer before that positive nucleus and that electron combines back, giving us more electrons that are available. The amount of loss to our radio waves increase as the frequency decreases. And as you go towards the Earth, the sun's energy becomes weaker and weaker as it's absorbed and as it interacts with the ionosphere. So let's look at the D region. This is the lowest region, 40 to 60 miles above the Earth, considered a daytime region. Generally, it has disappeared by about 30 minutes after sundown. Because it's so close to the Earth's surface, it has a density of atoms. This will cause ions to rapidly recombine back into a neutral particle. Radio waves here are absorbed rather than refracted. Carl, K9LA, calls it a giant attenuator and an RF sponge. However, the higher the frequency, the less that the D layer absorbs. So 160, 80, and 40 are drastically affected and are attenuated and have minimal propagation. Its chemistry is one of the most complex and one of the least understood. The E region, this is a fairly thin region. It's about 6 miles thick, and it's 60 to 70 miles above the surface of the Earth. We still have a pretty significant density, and electrons and positive ions still combine fairly quickly, but it will support some limited propagation. And normally the E region is associated with mainly daytime propagation. Within this, we have the sporadic E. This occurs about 65 miles up. It's the same height as the E layer, hence the name sporadic E. Comes and goes irregularly. In the literature that I've read, it's called regions, patches, clouds. They generally have a fairly well-defined geographical characteristic. They're fairly thin, and they're 50 to 100 miles wide. We think that they can move up to a few hundred miles an hour. Some of the current ideas, and actually there's been some new research that I've been hearing about in HAMSCI, but they're pretty sure that it's metallic ions from meters, plasma instability, and some disturbed magnetic activity. Now the F region. This is the one we love. The F1 and the F2. The F region actually at night will begin to shrink, and it becomes smaller from the bottom up, and it shrinks at about 700 meters a second. F1 rises and falls with the rise and the setting of the sun, generally disappears at night, fairly similar to the E layer. Maximum ionization for F1 is right around noon each day. F2 exists during the day and the night. This is the most ionized layer, and if you're a DXer, you love F2. It is in a constant state of motion. You have all kinds of things going on in it. Ionization increases just before sunrise. And the most electrons, and this electron density is found on winter days in F2. So that's the presentation. Let me put in a plug now. The solar eclipse QSO party will be in October 14th, when we have an annular solar eclipse where it's almost completely covered, but not quite, on October 14th, and then a total solar eclipse on April 8th of next year. These will be the last ones that go across the nation until 2044. It's a great chance to do some studying, and the shadow of the moon is going to create a temporary nightlight condition. This will cause the ionosphere to weaken, and it'll cause changes. At HAMSCI, we're planning on having these solar eclipse parties, contests, whatever you want to call them. And this will be an excellent chance to help science and the studies that are going on. There's a whole nother presentation just on this, and there's a lot of information on the HAMSCI website. But I know that one of the clubs I belong to, the Utah DX Club, we are planning on being involved with this, particularly where we're in Utah for the annular. And then another club I'm associated with, I think we're going to be able to put something together with them. Basically, we just want you on the air. Whisper, sideband, voice, Morse code. We want you on the air so that we can see the effect that these eclipses will have. And it gives us an ability to check other aspects of the ionosphere. Again, there's a whole presentation just on this. All I want to do is just touch bases, let you know it's coming, mark your calendar. It should be a pretty neat event, and to be able to be part of it would really contribute to what we have in science. There are some great resources if you want more, a lot more in depth. Carl, K9LA, Don, W3LPL, Contest University, Dr. Scove, all of those can give you a lot more in depth. And those are some of my references that I've got for this presentation. So with that, I have a few minutes before I have to take off. Again, let me say thanks for the opportunity to get to meet some of you, to do this presentation. My sincerest wish is that at least one person here tonight, when they go into a presentation on propagation, will have a better understanding on solar flares and CMEs and the ionosphere and things like that. And so that's what I really hope. So I can turn it open for a few minutes for questions. I'm going to quit sharing screen now.